Hello everyone, welcome to the channel. So in this video I'm going to show you how to calculate and export a Normalized Difference Vegetation Index and Soil Adjusted Vegetation Index and Normalized Difference Water Index from Landsat 8 Imagery in Google Earth Engine. So now let's get started. So vegetation and water bodies are essential components of the Earth system, and their monitoring is crucial for environmental management and agriculture, forestry and hydrology. The increasing availability of the satellite remote sensing data, particularly from the missions like Landsat 8, allows an accurate and consistent monitoring of these resources over space and time. So the vegetation indices and the water indices derived from the multispectral satellite imagery are widely used tools for assessing ecological condition. So among these, the Normalized Difference Vegetation Index and Soil Adjusted Vegetation Index and Normalized Difference Water Index are the three most commonly applied indices. So starting with the NDVI is the standard index to measure the vegetation greenness and biomass by contrasting the reflectance in the red and near infrared spectral regions. And next is the Soil Adjusted Vegetation Index, which improves the NDVI by correcting the influence of the soil brightness, especially useful in spare vegetation areas where the soil reflectance dominates. And last is the Normalized Difference Water Index, which detects the surface water moisture condition by contrasting the reflectance in the green and near infrared spectral bands. So now let me get back to Earth Engine. So first we're going to define our region of interest. So for example, I have already defined my region of interest here. So let me show you that. So my study region lies in the state of Tamil Nadu and Kerala here. So I'm going to select, let me show you that. So to define our region of interest, first we're going to navigate to this option called draw a rectangle. So I'm going to click this option called draw a rectangle. So once you click this option, we have the set of options that appears here. So now we are ready to draw a study region over our region of interest. So we're going to draw my study region over this part of the areas. So you can able to see I've created my region of interest. So in the next step, I'm going to exceed this. So once you create this polygon, in the top section, we have the new variable called variable geometry, which appears here. So we're going to replace the geometry name by AOI, that is region of interest. So I've replaced as this particular variable name as AOI. So this particular variable will be automatically reflected in this study region. So once we created our region of interest, in the next step, let me run this code here. I'm going to click this option called run. So now here we're going to navigate to the layer section here. So we're going to turn on study area L3. So you can able to see we have created our region of interest here. So once we created our region of interest, the next step we have to apply a set of we have to create a set of functions to apply the scaling and offset factor, and after that we have to apply the mask cloud and shadow cloud shadow to mask out the cloud and cloud shadow regions in our satellite imagery. So we have to apply two set of functions here. So starting with, we're going to apply the scaling factor to convert the digital number to a physical number. So let me show you that. So this is Landsat 8 level 2 collection to tier 1, and the dataset availability is from 2013 to 2025 here, and the dataset provider is USGS. And you can access this Landsat 8 imagery using this set of code here, that is Earth Engine Image Collection Landsat LC8 collection 2 tier 1 L2. And you can go through the description about this particular dataset. So the dataset contains atmospherically corrected surface reflectance, land surface temperature, derived from the data produced by Landsat 8 OLI TIRS sensor. So these images contains 5 visible and near infrared bands and 2 shortwave infrared bands processed to orthorectified surface reflectance, and 1 thermal band processed to orthorectified surface temperature. So they also contains an intermediate band used in the calculation of ST products as well as the QA bands. So the ST products represents the surface temperature product, and QA band which represents the quality attribute of the Landsat 8 imagery. So now let us go through the bands that is available. So starting with the resolution is around 30 meters, and these are the following set of optical bands that is available in this dataset here, starting with SRB1 to SRB7. So we have the scaling and offset factor. This is the scaling factor and this is the offset factor. So before proceeding towards any analysis, it is essential to apply the scaling and offset factor here. So scale factor of 2.75 into 10 power minus 5 and offset factor of minus 0.2 is the offset factor. And these are the bands. B1 represents the ultra blue coastal aerosol, and B2 is the surface reflectance blue, and B3 is green, and B4 is red, 5 is near infrared, 6 is short wave infrared 1, and 7 is short wave infrared 2. So now let me get back to Earth Engine. So here we are going to create a function to apply the scaling factor to our optical and thermal bands. So we're going to first apply this function called, create a function called apply image scaling and representing the image of Landsat 8 image. And the next step, we're going to select the optical bands to the scale optical bands to a reflectance value. So basically we're going to scale the optical bands to a reflectance value. So to do that, we're going to apply the scaling and offset factor. Starting with, we're going to define a variable called optical scaled is equals to, we're going to select the Landsat 8 image dot select SRB dot. So it's going to select all the surface reflectance band in the Landsat 8 imagery. And the next step, we're going to multiply the scaling factor, that is dot multiply 0.000275. And next we're going to add the offset factor, that is dot add minus 0.2. And similarly, if you're going to perform any analysis using a thermal band, so it is also essential to apply the scaling factor to the thermal band here. So the scaling factor for the thermal band, the SR-B10, so it's a surface temperature B10 band. So this is the scaling factor and offset factor. Scaling is 0.00341802 and offset factor is 149, and the units is in meter, and the wavelength is 10.60 to 11.19 microns, and band 10 represents the surface temperature. So we can apply scaling factor to this ST band 2. So to apply scaling factor to ST band, we're going to define a variable called thermal scaled is equals to image dot select. Image represents our Landsat. So the image which represents our Landsat 8 image, and we're going to mention dot select ST band. So it's going to select the surface temperature band, and we're going to multiply our scaling factor of 0.034180, and we're going to add our offset value dot add 149, and next we're going to replace the original band with the scaled band. So to do that, we're going to mention return image dot add bands. We're going to mention optical scale band. So now we are replaced with optical, and similarly we're going to add a bands called thermal bands. So to do that, we're going to mention add dot add bands thermal scaled. And similarly, we're going to apply a second function in order to mask out the clouds and cloud shadow in our Landsat 8 imagery using the QA pixel band. So to do that, we're going to mention another function called function apply cloud mask image collection, representing a Landsat 8 image. And next step, we're going to define a bit mask for the cloud shadow. The cloud shadow will be represented as bit 3, and the clouds will be represented as bit 5. And we're going to mention a variable called cloud shadow mask bit is equals to, so 3 is far greater than 1. And similarly, we're going to mention another variable called cloud mask bit is equals to 5 is far greater than 1. And next step, we're going to select the quality assessment band. That is, we're going to select this particular band called QA pixel band. So pixel quality attribute generated from the CF mask algorithm. So we're going to select this band here. So to select that, we're going to mention a variable called quality assessment is equals to the image collection dot select QA band. So we are selecting the QA band using the select function here dot select QA pixel band. And the next step, we're going to create a mask where both the cloud and cloud shadow bits are set to 0. So it means that it's going to mask out the clouds and cloud shadow areas in our Landsat 8 image. So to do that, we're going to mention a variable called clear sky mask is equals to quality assessment representing this particular variable, and we're going to apply a function called dot bitwise and. So we're going to mention dot bitwise and representing the cloud shadow mask bit variable, and we're going to set to 0. And similarly, I'm going to mention to another using dot and function the quality assessment representing this particular variable, and I'm going to mention dot bitwise and representing this variable called cloud mask bit that represents this particular one, where it's going to mask out the cloud contamination in the Landsat 8 image, and we're going to set to is equals to 0. So it's going to mask out all the clouds in the Landsat 8 image. And to apply this mask to the image, we're going to mention the return image collection dot update mask. So it's going to update, it's going to mask out all the cloud shadows and cloud areas in our Landsat 8 image using, we're going to mention it as dot update mask clear sky mask, representing this particular variable. We set to the cloud shadow mask to 0 as well as the cloud masks to 0. And the next step, we're going to import our Landsat 8 imagery, that is our surface reflectance imagery, into Earth Engine. So to do that, we're going to mention a variable Landsat is equals to Earth Engine dot image collection Landsat LC8 collection to tier 1 L2. So which represents this particular imagery. So this is our Landsat USGS Landsat 8 level 2 collection to tier 1. So availability, you can able to see that 2013 to 2025. And the dataset provider, this is the code I have used to access the Landsat 8 imagery in the Earth Engine. So in the next step, I'm going to filter it based on our region of interest. So our region of interest is represented in this. So in this boundary here, you can able to see that. So this is our study region. So I'm going to apply dot filter bound based on our region of interest, that is AOI, our area of interest. So using dot filter bound function AOI representing our variable we previously created here, the variable AOI. And next step, we're going to filter it based on the specific timeline of our choice here. So for example, I'm going to analyze within the set of period from 2023 to 2024, 2023 January 1 to 2024 December 31st. So to apply, select this temporal timeline, we're going to mention dot filter date 2023 January 1 to 2024 December 31st. And the next step, we're going to filter it based on our a cloud cover with cloud contamination less than 10. For that, we get as mention dot filter Earth Engine dot filter less than cloud cover of 10. So it's going to filter the Landsat imagery with the least cloud contamination, which is lesser than 10%. And last, we're going to apply the functions we created earlier. So where we're applying our scaling factor and the offset factor, as well as the to mask out the cloud and cloud shadow areas in the Landsat 8 imagery. So the first function, that is dot map apply image scaling, which apply the scaling and offset factor to a Landsat 8 image. And next set of it's gonna we're gonna apply the function that is dot map apply cloud mask. It's gonna mask out the cloud areas and cloud shadow areas. So once we apply this functions and scaling factor, we are ready to perform our analysis. So next step, we're gonna select. We're going to select the least cloudy image. For that, we're going to mention a variable called image is equals to Landsat dot sort cloud cover. And to get a mean imagery out of the entire collection, we're going to mention dot mean function. And the next step, to add this layer, we're going to mention dot map dot add layer image dot clip based on our region of interest. So we're going to clip it based on our region of interest using dot clip function. AOI, which is our region of interest. This is our region of area of interest, and using this following set of bands here. So to visualize it in true color composite, we're going to mention this set of visualization parameter. So we're going to mention the bands SRB4, SRB3 and SRB2, and it's going to give us a true color. In this combination, it's going to give us a true color composite image. And also we're going to set the minimum and maximum value, minimum 0 and the maximum of 0.3, and we're going to output the layer name as true color. So now let me run this code and let us visualize the result. So you can able to see this is our image, the true color composite image of Landsat 8 image for the selected study area. So you can able to see that. So you can also apply the stretch type by using navigating the option. We're going to click this option and I'm going to select the stretch 90% and I'm going to click apply here. So now you can able to visualize the Landsat 8 image. So now let me, I'm going to close this. So you can able to see this is our Landsat 8 image here. So in the next step, we're going to calculate the Normalized Difference Vegetation Index. So let me show you the formula. So this is the formula to calculate the Normalized Difference Vegetation Index. So NDVI is equals to NIR minus red divided by NIR plus red. So NIR, which represents the near infrared band, the band 5 in the Landsat 8, the high reflectance for healthy vegetation. So NIR high value, higher reflectance of NIR represents a healthy vegetation. And the red band, which represents the band 4 in Landsat 8, strongly absorbed by the chlorophyll in the plants. And the value range, if the value close to plus positive, it indicates dense vegetation, dense healthy vegetation. And the value near 0 indicates the barren land or the build-up surfaces. And if the value is near negative, it indicates the water, snow or clouds. So now let us perform NDVI. So to calculate NDVI, so this is the formula, and this is the formula where NIR is band 5 and the red is band 4. So we're going to mention a variable NDVI is equals to image, that is our Landsat 8 image dot normalized difference SRB5 and SRB4, which represents SRB5 minus SRB4 divided by SRB5 plus SRB4, and we're going to rename as NDVI. And similarly, to calculate the soil adjusted vegetation index, so this is soil adjusted vegetation index. So the formula to calculate the soil adjusted vegetation index, it involves, so NIR minus red divided by NIR plus red plus L multiplying 1 plus L. So here the L, which represents the soil brightness correction factor, so it has a value of 0.5. And this particular indices is useful in semi-arid and arid region where the soil reflectance can distort the NDVI value. And the ranges, so similar to NDVI but more reliable in spare vegetation and bare soil conditions. So this index is particularly useful in case of semi-arid and arid region where the soil reflectance can significantly distort the NDVI indices. So in that case, you can go for soil adjusted vegetation index with the soil brightness correction factor to be applied, and this is the common value of 0.5. So now let me get back to Earth Engine. So now to calculate the soil adjusted vegetation index, we're going to use this formula as I mentioned earlier, and here the L, we use the correction factor 0.5, the soil brightness correction factor. So I'm going to mention this formula here. Variable SAVI is equals to image, that is Landsat 8 image dot expression, we're going to mention NIR minus red divided by NIR plus red plus L and multiplying 1 plus L. And here the NIR represents we're going to select the band image dot select SRB5, and the red band which represents image dot, we're going to select SRB4, and last we're going to apply the correction factor, that is L, which represents the correction factor of 0.5. And we're going to rename as dot rename SAVI, that is soil adjusted vegetation index. So let us run this code and visualize the result here. So we're going to zoom in here. So first I'm going to turn off this particular one here. So first we are currently visualizing the NDVI value here. So we can able to see here all the white portions which indicates the bare soil and or build-up areas, and all the greener area which indicates the dense vegetation here. So we can able to see, and the white areas might indicates the bare soil or the water bodies too. So we're going to navigate to the layer section. I'm going to click this option, and I'm going to select the custom to be stretched 90%, and I'm going to click apply. So now here you can clearly able to visualize the difference. I'm going to turn to a satellite mode here, and let me close this, and you can able to see the difference. You can adjust the transparency here, so you can able to see all the blue areas which indicates the bare soil. So you can able to see that all the blue areas which indicates the bare soil, and as well as this set of blue areas which indicates the water bodies. So we can classify this image further based on this NDVI value to find out the bare soil as well as the water body, and all the vegetations are clearly highlighted in the green color, so you can able to see, and the bare soils are in white color. So you can able to see the difference here. Bare soil. So you can able to see here the bare soil which appears to be in blue in color, but the hard rocks or the exposed outcrops here, for example this areas which indicates the white in color, so which you can clearly distinguish from this image here, and the vegetations are clearly indicated in green color. So in the next step, next image is the soil adjusted vegetation index. So again, I'm going to navigate and turn on the soil adjusted vegetation index here. So from here, let me adjust the stretch type here. I'm going to select custom to be stretched 90% and I'm going to click apply. So the value ranges from positive value from 0.072 to 0.55. I'm going to click apply. So now you can clearly able to visualize greener areas, which indicates the vegetation, and more dense green, which represents the dense vegetation areas, and the exposed areas, which indicates the bare soil, and this yellowish, rather than red color, which represents red, and the yellowish color, which represents bare soil. And let us check me out what is the red color is. I'm gonna navigate to this layers and let me turn off this transparency. So for example, this particular area, it has a water body. So we're going to turn this transparency back to full. So all the red areas, which indicates the water bodies. So you can clearly able to see that all the red areas, which indicates the water body. And as well as here, you can able to see mostly the red areas, which indicates the water body, you can able to see. And similarly, let me zoom back out. So here, all the yellowish areas here, so you can able to see this yellowish areas, so which represents the hard rock here. So you can able to see, let me turn off this. So you can able to see this, I think is the weathered outcrops here, so which is in the color of yellowish color. And all the green, light green areas, which indicates the vegetation, and the dark dense vegetations are clearly indicated in dark green color. So this is the for SAVI. So the next is we're going to navigate to we're going to calculate. So the next we're going to calculate the normalized difference water index. So the normalized difference water index, which is represented in this formula here, that is NDWI is equals to green minus NIR divided by green plus NIR. So green band is band 3 in Landsat 8 image. The water reflects strongly in green wavelength, and which strongly reflects in the green wavelength, and NIR, which water absorbs strongly in NIR. So the ranges, the value close to positive 1 indicates the presence of water, and the value near 0 or the negative indicates the vegetation, soil or buildup plants. So now let me get back to Earth Engine. So here to calculate the NDWI, we're going to mention this is the formula to calculate NDWI. We're going to mention the variable NDWI is equals to image dot normalized SRB3 and SRB5. So SRB3 minus SRB5 divided, that is SRB3 minus SRB5 divided by SRB3 plus SRB5, and we're going to rename as NDWI. And last, to add this layer, we're going to mention map.add layer NDVI.clip based on our area of interest, with a set of a minimum of -1 to maximum +1, with the following set of color palettes from blue, white and green. So blue, which indicates lowest, and green, which indicates the highest, which follows for other layers too. And we're going to output the layer name as NDVI. Similar for steps, map.add layer that is soil adjusted vegetation index .clip based on region of interest, minimum and maximum value, and these are the colors of color palettes. And last is similar to NDWI. We're going to mention the map.add layer NDWI.clip based on our region of interest. We're going to set a minimum -1, a maximum +1. Color palette starting with the white blue. So NDWI represent two set of palettes. Blue, which represents water, white, which represents the non-water areas. And last, we're going to export this image. To export, I'm going to export this NDVI and soil adjusted vegetation index and NDWI. We're going to mention export.image.to drives. An image is NDVI. Description is Landsat 8 NDVI. Folder Earth Engine export. File name prefix is L8 NDVI. And region is AOI. Scale is 30 meters and max pixel value. This similar steps follows to other set of for SAVI as well as NDWI, except we're going to change this few changes here. So the description and file name prefix and the image. And similar to this too for NDWI2. So let us save this, and I'm gonna run this code. And once you click this option, we're going to navigate to the task section here. So we have this unsubmitted task called Landsat 8 NDVI and Soil Adjusted Vegetation Index and NDWI. So to export any image of your choice or all the image, you have to click this option run. So the window pop-up saying initiate image export, and task is Landsat 8 NDVI, coordinate reference system is EPSG 3857, spatial resolution is 30 meters. We can export to a drive with this Earth Engine export, and the file name is L8 NDVI, and file format is GeoTIFF. So to export this image to your drive, you have to follow click this option called run to export this image to your drive. So I'm going to cancel this. So similar steps to be followed to export other images too. You have to click run, and once you click this run, the image will be exported to a Google Drive, and where you can download this image. So in this video, I have shown you how to calculate and export NDVI and Soil Adjusted Vegetation Index and NDWI indices from Landsat 8 Imagery in Google Earth Engine. So thanks for watching, and make sure that you subscribe to our channel and give us a like.